Hello, everyone, and welcome to today's webinar, Mastering Product Consistency, the Power of Structured Problem Solving and Tackling Long-Standing Issues. My name is Sam, and I'm delighted to be your host for this session. Before we dive in, a quick note on how to enhance your webinar experience. Be sure to download any attachments we've shared. These include additional resources to support you and your journey to operational excellence. This webinar will also be available for rewatching, so don't hesitate to revisit it to catch up on anything you may have missed. And lastly, if you are inspired by today's session and want to learn more about Chartwell's technical problem-solving solutions, feel free to reach out. We would love to hear from you. I am thrilled to introduce our two exceptional speakers joining us today, Jacob Powell and Johnny Cunningham. Both are consultants here at Chartwell. Together today, they will bring insights from their expertise in technical problem solving to improve operational performance. And with that, thank you for joining, and let's get started.
Great. Well, let's start off the webinar today. This is the agenda for the session. We're going to go through a range of things related to fault tree modeling. And I'm going to kick us off at the start with a bit of motivation about why we should care about technical problem solving in the first place. So when I was thinking about what the goal of a manufacturing organization is, I put some words together, and I think this sort of summarizes it well. It's to effectively and efficiently make high quality products to satisfy some consumer demand. And manufacturing organizations will often do this by taking some raw materials, they will transform these in a value add way, and then they will sort of dispatch them to customers. And the main way to do that value add transformation is using some machines or assets. And when you have assets and machines, you're inevitably going to get technical problems. And so some sort of common problems that arise with assets might be related to regular downtime, and that can reduce a site's capacity, reduce its output. But you might also have problems that cause a quality issue, and that can ultimately reduce your product yield. And so whatever you're manufacturing, providing there are assets present, technical problems will arise, and solving these can really transform a site's operations. And I want to introduce fault tree modeling. This is the methodology that at Chartwell we have developed to solve these complex technical problems in a structured manner. And you might be thinking, great, I heard of a lot of different problem solving techniques. Perhaps you've heard of 5 whys or you've heard of the fishbone approach. But fault tree modeling is the most efficient and the most effective method to solve technical problems. And that's why we want to share this with you today. So there are 5 key steps to fault tree modeling that I'm going to walk us through, firstly on this slide, but then I'm going to take us through a number of case studies that show these in practice. So the first step is about defining the exact symptoms. This relates to understanding the problem in a huge amount of detail. So we can ask a number of structured questions to elicit exactly how the problem appears, and that relates to when it occurs, where it occurs, both in the product and in the process, but also looking at how the physical variable relates to its sort of actual value and also its control value. And the point I always like to come back to with question 1 is that we should have understood the problem in enough detail that we should be able to taste the problem. That is the amount of detail that we should understand the problem in. Secondly, we need to build the process model. This relates to understanding how the system is meant to work, how the asset is made, and how physically, what is the engineering behind the way that it works. And from this, we're able to understand the physical variables that exist and how they relate to one another. Now, this is a really crucial step because we use the output of this sort of process model in step 3, which is all about building a fault tree. And in this third step, we take the high level problem variable that we've identified in question 1, And we use the physical variables that we've identified in question 2, and we can break down this problem variable into its physical constituent variables. Now, what we're able to do at this point is go through each layer of variables and very easily say whether a variable is in control, out of control. And by doing this, we can quickly descend a tree of variables and we can find the root cause. Now, the power of the fault tree is that we will not sort of go down a rabbit hole and we won't spend all our time looking at one variable when in fact we could have ruled it out earlier. The fact that we use this hierarchy of variables means that it is the most efficient method of solving a technical problem. Now, steps 4 and 5 relate to once we've found the root cause. And in step 4, we should be able to explain the failure mode. And what this means is that by sort of putting our finger on the button of the physical problem variable that we've identified, we should be able to turn the problem on and off as at will and as desired. And this shows that we really understand the problem and we have got the correct root cause. And then last but definitely not least is all about implementing an improvement plan and putting mitigatory actions in place to prevent the problem from reoccurring. Now, we spend a lot of time on questions 1 to 4, but ultimately the success of question 5 is ultra important to ensuring that a problem is not just identified, but that it is solved and it never reoccurs in the future of this site. Great, so that's an overview of fault tree modeling. Like I said, this is a methodology that we have developed, and this is a methodology that we've used in a number of clients and have had much success. So I'm going to take us through an example to start off with. And this is an example with a biscuit manufacturer. So the challenge that this manufacturer had is that they had a long-standing technical problem. A key asset that they had on the production line frequently malfunctions, and this caused repeated downtime. And you can imagine all of those biscuits going to waste, and that was definitely a bad thing to see when the Chartwell team entered the production line. Now, we used fault tree modeling to solve this technical problem. And because we did questions 1 and 2 in sufficient detail, we didn't even need to use the later questions. So firstly, we defined the exact symptoms. Again, we used a detailed pattern of failure analysis to really understand what this problem looks like. And by doing this, we were able to identify that this failure actually occurred every 69 minutes. It wasn't randomly every 60 minutes and then sometimes every 30 minutes. It was exactly every 69 minutes. And this is perhaps a fact that the site team had overlooked in the first place. But understanding this precisely was crucial to solving the problem. And secondly, building the process model and understanding how this asset worked versus how it actually worked uncovered the fact that within the machine, there was a counter that every time a biscuit was processed, it was increased by 1. And due to the throughput of the line, every 69 minutes, the memory became full, the counter reached its limit, and the machine malfunctioned. Essentially, the machine crashed because the computer memory was full. And what we were able to do is, having got this to this root cause, is we were able to implement a simple solution of just increasing the computer memory, and this eliminated the problem from ever reoccurring. I think this case study shows why questions 1 and 2 are so important, because by doing these in sufficient detail, it will ensure that we don't sort of pursue question 3 unnecessarily. Right. I want to take us now on to the main case study of this webinar, and this relates to a recent project with an industrials manufacturer. Now, the challenge that this manufacturer had is that they had a cost savings target of 600,000 euros that needed to be met. And we arrived on site and we delivered a number of work streams. And one of these work streams was a 30% reduction in material giveaway through fault tree modeling. Now, material giveaway might not be a term that many people have heard of. So just to define it very quickly, giveaway refers to the difference between the product's actual weight and the minimum specification weight of that product. And so any deviation from that minimum specification weight essentially means that we are giving away raw material for free to the customer. And it's a form of waste that actually often goes unnoticed in many manufacturers. Now, to achieve this workstream goal of reducing material giveaway by 30%, we needed to solve two quite complex technical problems. These were relating to product variability, specifically inter-product variability and intra-product variability. I'm going to, again, define what this means because I appreciate that this might mean different things to different people, and it's good for us all to be on the same page here. So firstly, inter-product variability. Well, this is simply that there were differences in the material usage between final products. So you can imagine here maybe perhaps 4 final products, and they all had differing weights, even though they were the same products and they had gone through the same process. So this was inter-product variability that I'm sure many people are familiar with. The second one is perhaps one that people are less familiar with, and this relates to intra-product variability. And what this means is that there were differences in material usage within the final product. So if we just take one of those final products and say it was overall, it was 1.5 kilograms. If we split it in two, into 2 separate parts, right down the middle, and we weighed both of them, one of them would weigh 1 kilogram and the other one would weigh 0.5 kilograms. Now, you would have expected if there was even distribution of material usage within the final product, you would expect that these two halves should weigh the same, but they don't. And that is because of this intra-product variability that we saw on site. Now, these were both incredibly complex technical problems. And of course, we used fault tree modeling as the methodology to solve these problems and to improve the problems on the site. Now, I'm going to take a deep dive specifically here into the one on the left, and that is the inter-product variability. Great. So kicking off with FDM question 1, as mentioned earlier, we first need to define the exact symptoms. And so we define this problem in a great amount of detail, and we've put a simplified version of that summary on this slide here. So what is occurring? Well, we've got variability in the weight of final product, as I mentioned. When is it occurring? Well, it happens across all products, actually. There's no products that are better than others. And there's been no recent worsening of this issue. It's been fairly standard for a number of years now. What are the control limits and actual values? Well, the control limit here is that we should obviously have 0 standard deviation in final product weight. We don't want any inter-product variability. And the actual value is that we have between 11.5 and 13.5 standard deviation in the final product weight. And again, that obviously shows that our final product weight is out of control because it deviates from that control limit. And then where in the process must this be happening? Well, using logic, because we have a problem with the weight of the final products, we can deduce that the problem must occur in the stage where materials are weighed out, because that determines where sort of the weight of that final product. And using this last part of question 1 allows us to prioritize where we need to deep dive in question 2. Question 2, as I said earlier, is all about building a process model. And again, this is something that we did in a really deep amount of detail. And again, we've put a simplified version on the slide here. Just to walk you through how this factory works and how the assets are connected, we have a number of silos of raw material, and these are connected by ducting into some downstream processing assets. And raw material is stored within these silos, and then a fan allows this material to be pneumatically conveyed through the ducting and into the downstream processing assets. Now, again, we were able to understand all of the physical variables that existed, and were able to build that process model to understand how material should flow from the silos into the processing assets. And again, this got us ready to ask that question 3 are all about building the fault tree and building that hierarchy of physical variables. And so we built the fault tree. As you can see on the right, we've got a simplified version of that fault tree. But I think what this shows is the process that we go through. Like I said, we start off with that high-level problem variable, which in this instance was the variability in the weight between final products. And we can instantly mark that in red because we know it's out of control. We're then able to break this down into constituent physical variables. We're aiming for these to be mutually exclusive and collectively exhaustive. And we can measure each of these and check whether they're in control or out of control. So you can see that the first rung of variables, we were able to show that the weight of material transferred into the ducting from the silos was in control, but that the weight of blocked material present in the ducting was out of control. And this means that we don't get sucked into the rabbit hole of pursuing variables that are related to the variable on the left. Instead, we can sort of really dig deep into the ones that are on the right. And we were able to look at the variables that relate to the presence of blocked material in the ducting. Like I said, this is the new problem that we were trying to face. We were able to look at the variables that sat beneath the weight of blocked material present in the ducting. The first one of those is the speed of the airflow, and the second one is the flow rate of material into the ducting from the silo. And we were able to break both of these down into variables that we could actually change. The first one of these related to the speed of the airflow. We were able to upgrade the motor pulley size to increase the speed of airflow, and this allowed us to reduce the likelihood of blockages being present in the ducting. We were also able to decrease the flow rate of material into the ducting from the silo by simply reducing the size of silo apertures. And both of these two things combined that I've highlighted in bold there in the tree allowed us to have a real impact on the presence of blockages in the ducting and therefore reducing the variability in weight between the final products. Moving on to the next slide, we're able to see the impact of these identifying these root causes and the mitigations that we put in place on the sort of the key KPIs. So we were able to reduce the inter-product variability across 3 products, and this enabled us to meet that goal of reducing giveaway by 30%. And you can see that graph on the right there. We managed to take it from a baseline of around 6% down beyond that 30% reduction of just under 4.5%. And that's a really impressive result, and it speaks sort of volumes to the power of fault tree modeling and its use in really complex technical problems.
Thanks, Jacob. So we spent a lot of time going through the kind of key technical and structural aspects to problem-solving efforts, but we're going to spend the next few minutes looking at some of the key interpersonal factors that are critical for good problem solves. So firstly, most manufacturing sites have quite a distinct separation between production, engineering, and maintenance. This does have lots of structural benefits, but it can hamper problem-solving efforts without the good cohesion between groups. So when tackling manufacturing challenges, it's essential that we approach solutions from a holistic perspective, involving everyone in the team by leveraging the diverse expertise, and that will allow us to achieve some key benefits. The first one is getting real insight and data capture from ground zero. So this all begins with a clear understanding of the actual issues being faced on the shop floor, so we don't go trying to solve a problem that doesn't actually exist for the team on the floor, and then collecting data and insights from the ground up, making sure that we ensure solutions are rooted in the realities of daily operations. Again, so that we don't make a solution that actually, when we come to implement, the production team struggle to roll out. The next thing is operator-led trials. And this allows us to further our understanding of what's actually going on day to day. Again, operators play a key role here in understanding the nuances of the process they work with, spotting things that someone who only takes a snapshot of the machine or process might see. And by involving them in trials, we deepen our understanding for potential solutions and then create opportunities to refine them based on real-world feedback. Finally, getting into the shop floor allows an increased chance of sustaining the solutions. Lasting change requires especially a commitment of those who are most impacted and those who are going to be actually running machines day to day. So when the shop floor is invested in the solutions because they were part of bringing them together, they're more likely to sustain and champion the changes, and this ensures long-term success. So by fostering this collaboration, we can drive more effective, sustainable improvements and can continue to innovate within the manufacturing process. Now, I've talked a lot here about what the benefits are. This is the key role of the team lead in the problem-solving effort. And so what we try to do when we go on site and roll out these problem-solving changes is bring together these groups, again, which is often where we see teams fall down, even if they have the right structure behind the problem-solving effort. The next thing we need to do when we start a new problem solve is challenge assumptions. So when faced with complex problems, it is crucial to push beyond our current understanding of the process. Simply relying on what we already know can limit both our ability to find true solutions and then roll them out. This can often be why we see inefficient workarounds for long-standing issues, transition into day-to-day normality for sites, or even become an accepted issue that we just work with. So to solve these challenges effectively, we need to adapt a deeper and more systematic approach. So the first step to a good problem solve is resetting what we think we know. We must reset our thinking and look at the problem from a fresh perspective, free from preconceived notions. And this allows us to avoid biases that may have influenced our past decisions. And this also opens the door to innovative solutions. The next thing is building our understanding from first principles using a structured approach. Once we cleared away those assumptions, we can start from first principles, breaking down the problem into its core components using the structure that Jacob's already laid out. By approaching the issue step by step in a structured manner, we can rebuild our understanding of the process in a more accurate and comprehensive way, focused on actually solving the problem rather than just making the machines run day to day. Finally, at every step, we need to rigorously challenge our process knowledge. This is often the most difficult step when we've got a team that's got lots and lots of experience and feels they know how to work the machines very, very well. So this process doesn't end with initial analysis. At every step, we must challenge the process knowledge from like initial problem understanding to all the way through to solutions, asking tough questions and ensuring that each part of the solution is fully scrutinized. This rigorous approach allows us to avoid errors and identify opportunities for optimization that might otherwise have gone unnoticed. So by resetting, rebuilding, and then rigorously questioning as we go through, we unlock deeper insights that lead to more robust and effective solutions for even the most complex problems. The final key factor then is improvement attitudes and mindsets. Again, this is something we find that is very easy to lose when you've been on site for a long period of time and is essential to bring a fresh perspective. So when it comes to problem solving, the mindset we adopt can be even more powerful than the technical expertise, materials, or resources. And I know that sounds like a big statement, but hopefully it's become clear in a second. A strong solution-focused mindset drives, first of all, meaningful results. And this approach can be the difference between making short-term fixes that we think we come up with and then long-lasting improvements that everyone is truly bought into. So to harness the full potential of this mindset, we're going to focus on a few key factors. The first one is believing improvement is possible. Again, it sounds simple, but the foundation of any good, successful problem-solving effort begins with believing that that improvement is a real achievable thing that we can do. Without this belief, we limit our potential to find or innovate potential solutions. And when we truly believe that things can get better, we open up a world of possibilities and foster a culture of continuous improvement on sites. The next thing is taking ownership of progress. And this starts right at the top of the business, all the way down to the shop floor to make sure everyone's bought in. So solving problem efforts is a collective effort, but individual ownership is also critical. Each team member needs to be personally responsible for their own part in driving change, ensuring that we all contribute to moving the solution forward. This ownership creates accountability and motivates individuals to stay engaged throughout the whole process, from both problem solving to also implementing the solutions. Similar to this, we need to hold each other accountable. This accountability is a vital aspect of the success. And in a collaborative environment, it's important to not only hold ourselves account, but also each other account. This shared responsibility fosters trust and ensures everyone is committed to achieving the solution, while also encouraging higher standards for performance and integrity. The last thing then is solving to root cause. So rather than focusing on symptoms, which can often be very attractive and feel easier to come to a solution quickly, we must aim to solve the problem at its root cause. So first of all, this involves addressing the underlying issue, such that we can prevent reoccurring problems and create lasting solutions. Solving the root cause also requires a mindset of deep investigation and persistence, as it may take more time and effort, but leads to more effective long-term outcomes. So by fostering this mindset centered on belief, ownership, and root cause focus, we set the stage for an effective problem solve that creates lasting and meaningful improvements. So I focus a lot on the team-related benefits there and key parts of the team. Now we're going to focus on the role of leadership that might not necessarily be directly involved with the problem solve, but is absolutely critical to empower that team to generate a good result. So leaders often set the tone for how challenges are approached and ensure that the environment fosters creativity. In the context of problem solving, there are two key aspects we believe that the leadership must focus on. The first one is establishing a culture that doesn't fear. A fear of failure can stifle innovation and creativity, especially when tackling complex problems. We need our leaders to create a culture where failure is not seen as something to avoid, but a natural part of the learning process. As hopefully what you'll see when you try this out is lots and lots of steps throughout the way. We're going to hit roadblocks and we're going to experience failure that's going to be a part of the journey. So these problem-solving efforts often require teams to think outside the box and take risks by investigating trials that aren't guaranteed to succeed. And this requires an investment of both time and sometimes capital as well. So it needs that element of confidence from the leadership team to do this. So by supporting this mindset, leaders will encourage experimentation, creative thinking, and the willingness to push boundaries in pursuit of the best possible solutions. Again, this is an area where we often see teams fall down, where lots of innovative individuals on the shop floor don't necessarily feel empowered to investigate and solve the problems. The next thing is removing roadblocks and holding teams to account. This is a much more practical thing that leaders can do with a problem-solving effort. So as teams trial solutions, progress can often be hindered by roadblocks or delays that fall outside the immediate control of the problem-solving team. So we need leaders to be proactive in removing these roadblocks where the team necessarily isn't empowered to do that already. And this means securing resources sometimes and facilitating cross-departmental collaboration or making decisions that unblock the progress. At the same time, the leaders must hold the team, the direct team, accountable, ensuring that commitments are being met, actions are being taken in time, and this is being done in an effective manner. The balance of support and accountability ensures that this problem-solving effort remains focused, efficient, and productive without stalling on any personnel-related factors. So to re-emphasize, by establishing a culture that embraces failure as a learning opportunity, and by removing the roadblocks and holding the team accountable, leaders can empower their team to tackle challenges with confidence and determination. We think is really, really important to driving lasting change and implementing impactful solutions. So finally, some practical takeaways. Again, these are those things we hope that anyone watching this webinar can take away and roll out with their teams in the next couple of weeks or months if they think it's useful. So the first one we've got here is start small, think big. Some of the things we talked about today are really big, meaningful changes that we've been able to make as a result of FTM and problem solving. However, if you're just starting out on your FTM journey and want to build up a bit of confidence in your team, we recommend starting small, picking a problem that is not necessarily the most complex to solve, but can have a small amount of meaningful change, build some confidence, improve buy-in, and this will generate motivation to go after some really big complex problems that might require a bigger team, a longer period of investigation, and that initial momentum that might not necessarily have without some initial problem solves. The next thing is, I hope you kind of picked up from Jacob's piece at the start, was rigorously applying question 1 and 2 of FTM. What we often find with people trying to use FTM is that the fault tree model in question 3 can be the most attractive and an interesting thing to jump straight to. But it's really important to get as close to the problem as you possibly can in question 1 and 2 to build up that foundation for a good fault tree later on. Again, thinking, how does this process work? Which part of the process is failing and how is it supposed to work? The next thing is focusing on actionable levers. Now, going through the problem solve, it can often be easy to get really bought into the investigation itself and lose sight of the solutions at the end of the process. So when you're in the fault tree model aspect of the process, it's really important to think of variables and use variables that can act as levers for improvement, mainly so that you don't get to the stage of, we think we've solved this problem, but all the levers we've identified, we can't actually do anything about. Again, key things to think about here. making sure they're low cost and low complexity where possible, so that there's a minimum barrier to actually rolling out these solutions. And finally, the last thing we think is really important to sustain change in your sites is measuring what matters. So it's really important to use clear metrics to assess performance before and after applying FDM. This way we know if our solutions have been successful, and we can identify any recession to historic performance. Because what we often see is we get a great result off the back of a problem solve. Everyone's really excited to roll it out, but ultimately it takes sustained change of behavior to actually see that change stick. And having a good KPI, a good way to track if our progress is receding, is critical to making sure if there is any recession, we can react to that. So that brings us to the end of everything we've got today from the practical piece.
Thanks so much, Johnny. I think we actually have time for a couple of questions. So let me go grab those really quickly from the audience. All right, it looks like the first question is for you, Jacob. In your experience, when it comes to the fault tree modeling approach, can fault tree modeling actually be utilized in other industries like the pharmaceutical industry or others that might be more rigorous or have a lot more rules and restrictions and regulations associated with them?
Yeah, I think the beauty of fault tree modeling is that it can be used in any industry, in any walk of life. I mean, it can be used if your boiler breaks down in your apartment, but it can also be used in a multi-billion-dollar pharmaceutical factory. If there is a problem, a technical problem, then fault tree modeling is the most efficient and most effective way to solve that problem. And I mean, at Chartwell, we've had many instances where we've gone after really complex problems in a wide range of industries, like we mentioned in this webinar, in industrials, but also in pharmaceuticals and food, as mentioned earlier. So it really is a methodology that can be applied in all areas and in all industries.
Perfect. And we have another question, and this one I think is for you, Johnny. So when you spoke about the importance of the entire team in technical problem solving and leadership's role in helping to facilitate that, how can we ensure as manufacturing leaders that our teams feel supported enough to take those risks and experiment while also maintaining that accountability you spoke about for the results?
Yeah, it's a good question. I think it's a tricky one for sure, and often where we see people struggle on site. I think that the first thing you can do is setting really clear expectations as a leader, creating that space for teams to experiment and try things out, but also being very clear where the boundaries are and what meets a failure and what's a success. The next thing I think you can look at is making sure you've got really regular check-ins so that you don't have a team get a long way down the problem solving effort, realizing they've gotten a long way beyond the expectations or outside the boundaries that have been set at the start, and you can kind of nip that in the bud quickly and make sure that the progress is along with your expectations. And then I think finally, and I think the most important thing is making sure we celebrate progress and not just success. Which again is very easy to lose sight of if you're only seeing the big picture or the higher level picture. But making sure that as we're going through the problem solving effort, where there is progress that doesn't necessarily generate a financial impact, we're celebrating that progress towards a solution that will generate that financial impact that is necessarily the kind of key end result.
Oh, perfect. Thank you. It looks like we are just at time. So thank you both for joining us today. It was really insightful, especially for me learning about fault tree modeling myself. For any of you who are still with us now, if you have any questions, feel free to get in touch and we'll be providing the additional materials at the end of this session. Thanks so much and have a wonderful day.